Section 10.1 Multiple Predictors, Video 5. In the previous video, we tested the effectiveness of one predictor by testing whether or not that predictor's slope was equal to 0. But what if we want to test the entire model? In other words, testing if all the predictors are effective as a collection of predictors instead of individual predictors. We can do that using an analysis of variance test, ANOVA. For the hypotheses, the null hypothesis is all the slopes are 0. In words, the model is ineffective. The alternative would be, well, at least one of them is not 0. And I do have a subscript of I here, because even though the generic last subscript up here is k, 1, 2, 3, k total explanatory variables, we don't know which one might not be 0, so we just generically say the ith one somewhere between 1 and k is not equal to 0. There may be more than one of them that's not 0, but it only takes one of them not being 0 to conclude that the model is effective. And the ANOVA table is the same as it was before, except the degrees of freedom column. In a simple regressions ANOVA table, the degrees of freedom for the model was 1 because there was only one predictor, but now we have k predictors, so it makes sense that this degrees of freedom is k. The total degrees of freedom is still n minus 1, and so the degrees of freedom for the error has to be n minus k minus 1 in order to preserve the additivity. In other words, if I add these two degrees of freedom, the k's cancel and it gives me the total degrees of freedom. But other than that, the construct of the ANOVA table is exactly like it was before. We'll get into the specific example for a moment, but what I mean by the construct of the ANOVA table is that the sum of squares are additive, so the sum of squares for the model plus the sum of squares for the error gives the total sum of squares. There are individual formulas for each of those sum of squares. They're on page 617 if you would like to take a look at them, but it's not something I will hold you accountable for. To calculate the mean sum of squares for both model and errors, you just divide the sum of squares by the degrees of freedom. Excuse me, let me take a drink real quick. The silver can is a Diet Pepsi, not a Coors Light. For example, the MS model is the SS model divided by the degrees of freedom, and the MS error is the SS error divided by its degrees of freedom. And the formula for the F statistic is still the ratio of the MS's, MS error divided by, MS model divided by MS error. And then the p-value is the area of the tail cut off by the test statistic. So let's look at this specific example. In the previous videos, I've been doing a multiple regression that only had 2 explanatory variables. We were attempting to predict the price of a printer based on its printing speed in pages per minute and the cost to print one black and white page. However, when I pulled the data set off of the website, there were actually 4 predictors I could play with. The 2 previously mentioned one, the cost to print one page in color, and is it the time or the cost to print a photo? I forgot which one it was. It was the time to print a colored picture, a photo. So printing speed, time to print a picture. Does not say what the time is measured in, but I might be able to make a good, I think it's measured in minutes based on what I can infer from in the book. But regardless, and these are the cost of printing a black and white page and a color page. So now let's look at everything they gave us. And here's the ANOVA output, which I generated in Microsoft Excel. You'll notice that the degrees of freedom is 4 because there were 4 predictors. The total degrees of freedom is 19 because there were 20 printers, as was alluded to in a previous video. So let's answer the question, is the model effective? You know, it's kind of funny that the question is a simple yes or no, and we're giving all this information and use almost none of it. We could do the critical value approach, but I would have to give you a critical value to compare this test statistic to. But we're given the p-value, and the p-value is less than 5%. since the p-value is less than 5%, we reject the null hypothesis. Reject the null hypothesis. And the conclusion is that the model is effective. Now be careful. That does not mean that every predictor is effective. That means that collectively they are. How can we tell whether or not an individual predictor would be effective? Well, then we would have to look at the regression output and look at that individual predictor's p-value. I happen to have them here, and in fact, I'm going to turn my computer around and show you what I'm looking at. What you see here, if I can get everything lined up well, that's good enough, is the ANOVA output up here, and below here is the regression output. Now, Excel gives you a lot of information we don't need, such as these numbers which represent confidence and prediction intervals, but let's not worry about those because I wouldn't give you those. And the variables were represented generically, but they're in the same order that I wrote them in the equation, ppm. In fact, let me go over here and just fix that real quick. This was ppm, this was photo, this was cost, oops, let off that cap key, cost BW, and this was cost color, just for a little more clarity. So if we wanted to test the effectiveness of the entire model, we would go to the ANOVA output and just look at the p-value, which is this. It doesn't say p-value, so we'll just make it say p-value real quick. I'll borrow that one. There. So you would just look at the p-value, and you'll notice on the board I had rounded it off to 3 decimal places, but regardless, it's still less than 5%. But if we wanted to test the individual predictors, we would have to go to the regression output and look at their p-values. So let's start with the p-value for the printing speed. Less than 5%, it's effective. Look at the p-value for photo. Way not less than 5%. In fact, it's almost 100%. So the time to print a photo is not an effective predictor because its p-value is too big. In fact, if you notice, all these p-values are too big. Now, previously, when we were just testing, or when we were just using printing speed, which is row 18, and the cost to print a black and white page, both of those p-values were less than 5%, and as a consequence, both of those predictors were effective when the model only included printing speed and the cost to print a black and white page. But when we bring in the other predictors, the time to print a color photo and the cost to print a color page, now the cost to print a black and white page is no longer an effective predictor. Basically, its effectiveness got spread around the other guys, and now they're all ineffective because all their p-values are too big. So you can tell that when you run a multiple regression, if you just use some of the variables and not all of them, you can get different interpretations and different results. But the more variables you bring in, then the less effective some of them may be individually within the whole picture. So to conclude this video, if you want to test the effectiveness of an entire model, look at the ANOVA table. If the p-value is less than 5%, the entire model is effective, even if not all the predictors are. Because if we looked at each predictor's p-value individually, only one of them is effective, the printing speed. Fascinating.